Next topic is Chapter 6, Thermochemistry. This is the only chapter that's going to be on exam 4. I think that's right, 4. Yeah, exam 4. So what comes to mind with thermochemistry? You know chemistry already. The thermo's the part. Okay? Just heat. Okay? We're gonna look at chemical reactions and transfers of energy during those reactions. This particular chapter is an introduction to a broader topic called thermodynamics. We're only going to focus on one little part of thermodynamics because if you try to digest thermodynamics all in one swoop, it can overwhelm you. So we're going to go into just talk about the thermochemistry applications and some ways to use what we know to solve problems. Even stoichiometry enters in. All right. So energy. Does anybody have energy defined at an earlier age? Energy is the capacity to do work or to produce heat. Those are the two characteristics where we have E represented by energy represented by E and capacity to do work, and we give that a little W. And heat, we give a little Q. All right, so those are the three main terms we're going to focus on for now. The law of conservation of energy was, it's not new, right? It came along fairly early, say in the mid to late 1700s. And all it says is that during a chemical reaction, energy cannot be created or destroyed. It can only be converted, transferred from one form into another. And this is actually another way of stating the first law of thermodynamics, which is that the total energy content of the universe is constant. All the energy it started with is the same amount of energy it has now. And sometimes you'll see it written this way. The change in energy for the universe is 0. There's no change in energy for the universe. All right. There are very few chemical or physical processes, for that matter, that occur that do not involve a transfer of energy. Right? There are very few exceptions to the rule that I could say all chemical or physical processes involve a transfer of energy. And I'd be 99.9% correct. There are a few exceptions, but very few. Okay, so we can, to understand how this energy is transferred from one place to another, one form to another, we need to get a mental picture of what types of energy are being discussed. Potential energy is just that. It's the potential to do work or produce heat. There's more to it than that. And we often just say PE for potential energy. Let's see, somebody dinged in. Maybe somebody dinged out and back in. That happens. Oh, there's Kathy. All right. We are a class today. Potential energy is potential to do work or produce heat. Can be divided into several types also. One of the easiest to understand is positional potential energy. And when we talk about positional potential energy, there's always one other factor involved, and that's gravity. So you have to be near some heavenly body that has enough mass to create a gravity well, so to speak. The Earth has gravity that we're used to. Right? On the moon, the gravity well would be less. It would be about 1/6 of the acceleration due to gravity on the moon. So once you consider the gravitational forces involved, then you can define positional potential energy. If I'm close to the body, like I'm on the surface of the Earth, and I climb a ladder or I climb up on the roof of the building, it takes an expenditure of energy. And that energy that I expended in order to do that is stored, partially stored in my position. Right? And you can get that energy back. Right? I've stored energy, say I get up on the top of the building. I've had to exert myself, use energy to get there. And if I want to get the energy back due to my position, all I have to do is jump off the building. Right? And when I hit the ground, I'll get all the energy back. Only the results might not be what I desire. I may break a leg or bust my head or compress my spine or something like that. But the energy, as far as the energy is concerned, it doesn't matter, right? I stored it going up and I got it back coming down. There's also compositional potential energy. This is the one that's more, this is a physical phenomenon. This is chemical. The composition of a compound can also store energy, right? One of my favorites is nitroglycerin. Right? Nitroglycerin stores a huge amount of energy in that little molecule. And we expend energy to build the molecule and store that energy in those bonds. And when those bonds break and form products, it gives up a lot of energy. Right? Some of it in the form of heat, some of it in the form of expanding gases. But that compositional energy is stored in the bonds. There are some others, right? The one we're primarily interested in is in chemical energy with the bonding. But you can store energy in an electrostatic field. If we, that's a little easy. It's more difficult to understand electrostatic field than it is magnetic. If you take two magnets together and you know which is the north and the south poles, if you put the north and south poles together, you know, it snaps them together. And then it takes energy to pull them apart. Well, you've lost energy when they snap together. And you have to put energy into them to bring them apart. And you're storing energy in their position. Yeah, it's kind of a cross between 1 and 2. If you, on the other hand, if you put north to north and they repel one another, then in order to get them together, you have to force them together. And for that, you're storing energy in the composition, in the structure of the magnets, how they're put together. You can store energy in a rubber band. See, I got one over here. This is one of those hypoallergenic bands. It's not made of latex. If I stretch it, I'm storing energy in that band. And to get it back, all I have to do is turn loose. And I feel the energy release against this finger. You can also have compositional energy based upon heat differences, right? The heat difference between the inside of your engine and the outside of your engine when your engine's running is a form of energy that is based upon that temperature difference between the two. And there was a lot of work done on that in the early 19th century. And that's when thermodynamics itself started to take root. There's also nuclear energy that stores energy. Now, it's a little more difficult to understand that one because until Einstein came along, we didn't really know what composition was responsible for all that energy, because the nuclear energy is massive compared to the mass of its origin. Right? So if you have one nucleus over here, and let's say you have two nuclei over here, right? So we split that, and that's what's done with U-235. Right? It splits into two smaller atoms at the nuclear, all right, its nucleus splits. Well, the difference between the two is this has mass, a certain mass of, let's say this is the origin, the original mass. Then we have these two masses over here, mass 1 and mass 2. If you add those two together, this mass is greater than those two together. Okay? That's where the energy came from. The difference in mass, the lost mass between these two is it's right there. And this is the energy equivalent of that mass. Okay? So if it doesn't strike you as odd that the law of conservation of energy doesn't hold, right? Because we have a certain energy here and we have a certain energy there. We don't have the same energy over here. We have more energy on this side because we've converted some of the mass. Right? So that's where the law of conservation of energy kind of breaks down, because matter and energy are interchangeable. So when you think of it in those terms, right, everybody knows current theory is that the Big Bang is when the universe started. Well, theoretically, at the very beginning, there was nothing but energy, only energy. And then very shortly, some of that energy started to be converted into mass. So if you think of it in those terms, that the original energy of the universe is the same energy we have now, only some of it's in mass, then the conservation of energy, that law, tends to hold water again. All right. So we've got potential energy. Now, does anybody have any idea what other kind of energy? How about kinetic energy? We've mentioned this one before. Kinetic energy is the energy of motion. Okay. So all we need to define energy of motion is we need to know the mass of the object and its velocity squared. And that will tell you the kinetic energy of any object in the universe. Now we can attribute kinetic energy to heat, because unless an object is at absolute zero, it's going to be moving. Right? Only at absolute zero would the object be perfectly still, have no kinetic energy whatsoever. So, for all intents and purposes, everything has kinetic energy. And the average kinetic energy of a collection of objects is defined by their temperature. Right? So if we know the temperature, we have an indicator, a way of quantifying the kinetic energy without actually calculating the kinetic energy of all the particles that are in the substance. But our key here is temperature. All right. So let's look at this example. This object at position A has a certain amount of positional potential energy. right? Because it's up here higher than the bottom of the hill. So we can express that difference in height in terms of potential energy. If we turn loose of it, right, it may impact B. Right? These are two separate objects. If A hits B and the transfer is completely elastic, that is, there's no loss of kinetic energy when they collide, then when A hits B, we would expect B to rise from this position up to this level where A is now. Okay? So this is what actually happens. When A hits B, B only goes up to that first level, right? So if we're going to conserve energy, where'd that energy go? Right? We converted potential energy to kinetic energy for A because it was moving at the bottom of the hill. But when it transferred its energy to B and gave B all of its kinetic energy, supposedly, it only went up to the first level. So where did all that extra energy go? If it was perfectly elastic, I mean, if we converted all the energy from A into B, then B should be up on the top level. But it's not. So where'd that energy go? It turned into heat, right? Due to friction. Now, we normally think of friction as, right, we have this surface here, and we have an object in contact with it, and we're applying a force to move it. Right? And the resistance to that movement is friction. Right? We can quantify what that force is. But for our purposes, you can also have internal friction. Right? When we try to push against an object and it gives a little bit, then we're making those molecules and atoms rub past one another. And there is contact internally. So what we've done is we've expended some of that energy that A had originally in giving it up with rolling friction, right? As A rolled down and B rolled back up, and internal friction of both A and B when they collided. Right? But the total energy that we started with is still there in some form or another. Does that make any sense or blow anybody's mind? We're starting off simple. Let's see. All right. We need to clarify some things here. It's a common misconception to go as far as to equate temperature with heat, but they're not the same. They are related, and we get a handle on quantify heat based upon temperature difference, but they're two entirely different animals. Temperature is an intensive property. In other words, the temperature of this, say I have a gas in a container. If I stick a thermometer in this side, measure a temperature at, say, 30 degrees Celsius. I stick it in the other side, it's going to give me 30 degrees Celsius. Doesn't matter. If I have that sample, if I have another sample that's this big, it's at the same temperature, it doesn't matter how much I have. It's an intensive property. And it's based upon the random motion of the molecules, the average kinetic energy of all the molecules in the container. Yeah, that's what I said. Whereas heat is, temperature can be measured in a static situation. But heat can only be measured when energy is transferred. It goes from one place to another. I think that's probably the key there. That's why I underlined it. Heat is a measure of the transfer of energy between two objects or two substances. And they have to be at different temperatures in order for the heat to move. So that's where the connection is. Right? Heat only moves from high temperature to low temperature. And when you think about it, right, if we have these two containers, let's say two gases in them, like that, and we had this one over here, and these guys were moving just really slowly. Right? They were hardly moving at all. These guys have lots of kinetic energy. And you know what that means? That means higher temperature. Right? So this temperature is greater than this temperature. So what happens if this wall is elastic, so to speak? In other words, if one of these strikes like that, then it'll transfer its energy to this side. Right? But these guys are moving so slow, if they happen to arrive at the same time, then what's the exchange of kinetic energy is going to be from the larger to the smaller, correct? Yeah. So heat transfer is between high temperature toward low temperature. Now you may wonder, okay, if that's true, how does my air conditioner work? Right? Because it takes heat from inside the house and sends it out. Right? In order to do that, you have to couple two processes. One process that transfers heat from a high temperature to a low temperature. In other words, from the freon to the air in the outside. Right? So your freon is heated up, and then it's transferred outside. But how did it get heated up? Well, it came from inside your house, where it was colder than the temperature in your house. So the heat transferred from your house into the freon, made it hotter than the outside. Then when it got outside, it transferred that energy to the air. So in effect, you're transferring from, in two steps, you're transferring from a higher temperature to a lower temperature. And then this lower temperature is higher than the outside, so it transfers its heat. So you have to couple the two in order to get that process. So we're not defying any of these concepts that we're learning right now. All right. So again, we have to have a temperature difference. Now, I'm going to look at these terms here. And we're going back to basics. And if you've never had physics, you're going to get a little bit of it now. Not a whole lot, just enough to help us understand the thermo part of chemistry. Work by definition, this one right here, equals a force times a distance. What that means is, if a force is applied to an object and it moves, then work is being done. And we can quantify that work by measuring how far it moves, and the force required to move it. Okay? So if I stand here and push on this wall, I'm not doing any work because that wall is not going to move. Right? But am I expending energy? Sure. Right? My muscles are tensing. I'm using up some ATP, right? Stored energy, and then if I keep pushing, then I'm going to have to go down the line and convert some glycogen into ATP, glucose, and then ATP, and expend more energy. And eventually my muscles will fatigue. But I'm not doing any work because nothing moved. I'm applying a force, but that's zero. So we have to have both the force and the distance moved in order to measure work in its most basic form. Here it is. Okay. Right now, I want to shift gears just a little bit and talk about the difference between state and path. We've mentioned this before. A state is just where it is now. We did this with gases, right? When we were trying to figure out whether it was a before and after situation or a state situation. Remember that? When you're trying to figure out, can I use the gas laws of Boyle's, Charles, Avogadro, or the combined law for a before and after situation? And if I can't, if there's only information given about the conditions right now, that's a state. We're right there and we don't know how we got there. So with that in mind, when we talk about energy, it is a function. In other words, it enters into equations. All right? And energy, spell. Energy is a state function. Now I'm going to expand a little bit. A state function is any function that only requires that you know where it started and where it ended. So in that respect, it's kind of like a before and after. But it doesn't matter how it got there. It could go all different places. It's just we know what it was here, we know what it is here. That's a state function in reference to energy. What was its energy at this position or time? What's its energy at this position? And the difference between the two is the change in energy. Okay? It's a state function. Whereas work, by contrast, is a path function. This is a state function. Work is a path function. It does matter how you get from point A to point B. If I go, let's see, if I take the interstate from Charleston to here, I've got to go up in about 2,000 feet elevation change between Charleston and here. If I take the freeway, there's a certain amount of energy I have to expend to get from this height to that height. Right? And that can be quantified as the force required to move my vehicle and me and everything in it, that distance. Okay, so that's the path that I took. If they shut the interstate down and we have to go the old roads, right? I don't know, I wasn't around for that. Do you remember the old times, the old days when you had to squirrel your way back through the mountains to get down there? Okay. Well, if you do, it's a more circuitous route. Say I have to go to Oak Hill and then down to Montgomery, is it? And then from Montgomery into Charleston. That would be a longer route. A longer distance with similar forces would take more work to do that. Or to come back, I should say come back. Right. I was coming up from Charleston, now I'm coming back from Charleston. Along the river first it is right, Montgomery. Isn't that where Tech used to be? Okay. And then go back up through the windy roads to get to Oak Hill and then back along 19 to get back to Beckley and meet at the same point as we did before. That path is a different path and it takes a different amount of work to do that. That's a path function. It does depend on the path that's taken to get there. Heat is similar, right? So these two are path functions. It does matter the path that's taken to get from one point A to point B. Whereas energy is only a state function. You need to know here and there. So the energy difference, the potential energy difference between where I was in Charleston and where I am now would be a difference in 2,000 feet. And the force I'm working against is gravity. And I'm storing energy in my position from there to here. All right. Yeah, that's right. And the path function does depend on the past and the path that it took to get from one place to another. All right. So let's set that aside for now. We'll come back to it later. Let's see how we're doing. We're doing good. So now we need to define some terms. If we're going to talk about transfer of energy, transfer of heat in particular, between a cold temperature region and between a hot temperature region to a cold temperature region, we need to define our terms. A system, what we're saying is a system is the part of the universe that we define. We focus our attention on the system. Sometimes the system is defined for us by the process we're investigating. Sometimes we just have to make it up. Otherwise, we're stuck in the mud. So this would be our system, whatever we define as our system. Everything else is surroundings. Okay? And this, of course, is the boundary between the two. All right? Surroundings. That can mean everything else in the universe. The problem with that is we don't have access to everything else in the universe. Right? It's a little more difficult. So what we often do, let me see if I'm getting ahead of myself. What we often do is we draw another boundary here. Now we have a system, surroundings, and the surroundings and the system together are isolated from the rest of the universe. Okay? Nothing gets across this boundary. Matter doesn't cross the boundary, energy doesn't cross the boundary. We are completely isolated from the rest of the universe. Now we can define what this is in terms of its mass or volume or whatever other factors we want to include, and we can define our system. Okay? Now, we can describe this system based upon this boundary right here. If this boundary is open, then both matter and energy can cross. Right? So energy can go backwards and forwards, or matter, mass, can go backwards and forwards if it's open. Okay? Some systems are like that, right? They have a boundary, but it's completely open and transparent to movement of energy and matter. That's not very useful for us. We need a little bit more control. So another way is a closed system. And a closed system removes the matter transfer. Now, anything that's in here stays in here, anything there stays there, and they don't cross. So that one is a closed system. Okay? Now the other one, the other possibility is we don't let energy cross that barrier either. Okay? And that's called an isolated system. No exchange of energy or matter. Now that's it. That's effectively what we've done with this outer boundary of the surroundings. We have isolated it from the rest of the universe. But you can also isolate the system from the surroundings. And in fact, our experiment next week, where we use styrofoam cups, if you have a chance to look at the procedure, we use styrofoam cups as our calorimeter, which is a fancy word for a heat measure. We use 2 styrofoam cups to isolate our system from all the surroundings. And that way, anything that happens in Vegas stays in Vegas. Okay, it'll become obvious to you, and I'll point it out again, why that's important for problem solving. Right, so we'll come back to that. All right. Now, when we talk about energy transfer, and we can say, let's say we've got a closed system. That is, no matter transfer, just energy. So if we allow energy to oh, by the way, when we define the movement of energy, it's always in reference to the system. So when we say endothermic, into thermic means into the system. So energy goes into the system, and we're going to focus on heat. Right? So if I put a Q there, energy moves into the system. All right, we can quantify that with numbers. We can say how many joules per mole, or whatever. How many joules move into the system? Well, in reference to the system, what's happening? What does the system see? System sees an increase in energy, right, as we move it in. So that means this value would have a positive. It would be a positive number. We went the other direction. If heat went out, then that would be, you put it over here, that would be a negative because the system would be losing heat. Okay? All right. Endothermic reactions absorb energy from the surroundings. Exothermic means out of, exo, and the system would be losing heat to the surroundings. What we also know is that when this energy moves, the amount of energy, because of the conservation of energy moving out of the system into the surroundings, the same amount of energy gained by the surroundings is the same amount of energy lost by the system. Just we can sort of keep a budget. Now let's see. The freezing of water, is it an endothermic or an exothermic process? Right. First thing you have to do is define what's your system. The system is your mass of water, right? Because we're talking about the freezing of water. So when water freezes, it's going from a liquid state to a solid state. Does it have to gain or lose energy to do that? If it's going from a liquid state to a solid state, it has to lose energy, right? Like you does anybody here still use ice trays in their refrigerator? Or does everybody have automatic ice makers? Okay. When that automatic ice maker fills up with water and it freezes, what's happening to the energy inside the liquid water? It's leaving, isn't it? Energy has to leave that water, which is the system. Energy has to be removed from the water in order for it to freeze. So that process is exothermic, right? We typically think of exothermic as if you touch it, it's hot. But it's only hot if it's hotter than your hand is. So that's a little misleading. We have to think of it in terms of the abstract, right? What's happening to it as it goes from liquid to solid? Well, it has to lose energy in order to become a solid. Because if it's liquid, it's at a higher temperature than the solid. And that means it has more kinetic energy in its molecules. So we have to slow the molecules down so they can start to attract one another. And that's what happens when you go from liquid water to ice. Slow the molecules down, and they have to lose energy to do that.
So then I guess whenever the water evaporates, does that mean it's an endothermic energy then?
Yeah. If it goes this direction to a gas, we have to add energy. So the Q on this side would be negative, and the Q on this side would be positive. You have to add energy to make it go to a gas. Exactly right. Okay, we define the system. We define the surround, well, we didn't actually say much about the surroundings, but whatever the surroundings are, we sort of implied the surroundings are the inside of your freezer where we put the water in the ice maker. And the heat is flowing out of the system to make it freeze. All right. So let's try some others. Let's see, let's clean this up a little bit. So classify each of these as exothermic or endothermic. The system is underlying force. So that way we don't have to jockey around and decide for ourselves. Your hand gets cold when you touch ice. Your hand is the system. If it's getting cold, if you feel it getting cold when you touch ice, where's the heat going? From the system. It's going out of the system, isn't it? It's exothermic process. Yep. Ice gets warmer when you touch it. Now we're talking about the ice when I touch it. If the ice gets warmer, it absorbs energy from my hand. In that case, it's endothermic. So it all depends on your perspective, right? All right. Water boils in a kettle being heated on a stove. We just talked about that. That has to be endothermic. Energy goes into the water to make it turn into a vapor. How about water vapor condenses on a cold pipe? Yeah, water vapor has to lose energy to become a liquid from a gas. Right? So it is exothermic. And ice cream melts. It absorbs energy from the air or the sun on a hot day when you're trying to eat it before it melts away. So that's an endothermic. You got to add energy to that ice cream to melt it. All right. Let's see. For each of the following, define a system and its surroundings and give the direction of energy transfer. In this case, we get to define what the system is. And it's instructive to think about what the situation is and actually which way is most useful in explaining the process. So we say methane is burning in a Bunsen burner in a laboratory. So what is the system? Did I lose somebody? No, I didn't lose anybody. Maybe they went away and came back. So we've got a Bunsen burner. Right here. Right there. And we got a gas delivery here. And we have this, like that ring around it that opens and closes the air inlet. So once the gas goes in and the air comes in, we have our system in here. We have our mixture of air plus gas. And then once we light it, we get this flame, if it's properly adjusted, that has a structure to it. Okay? So as the methane burns, what is the system? The system is the air-gas mixture from here all the way up into where it is combusted. Right? Because what we've got is methane gas plus oxygen gas yields carbon dioxide gas and water gas. Okay, so our system is the mixture of air or oxygen and gas, correct? And we know that we can measure the temperature, right, with a thermometer, as long as it's rated for that high temperature. Or you can feel heat coming off of it. So you know it's expending heat, right? As it burns, this Q is leaving the system. Excuse me, negative. Negative losing the system. So the Q is a negative value. It's giving up heat from the system during the reaction. How about water drops sitting on your skin after swimming and they evaporate? Okay, so what's the system in this case? Do I need to draw a hand? Oops, that's too big. That's my little finger in there. 1, 2, 3, oops. 1, 2, 3, 4, 5. Yeah. It's not a cartoon hand with only 3 or 4 fingers. Right? If you got water drops sitting on your hand and they evaporate, what's the system? What would be most useful to understand this process? Define the system as water droplets. Right? Water is the system. So if water is the system and it evaporates, it's absorbing heat from my hand. So my hand is the surroundings and heat's moving into the system. Right? That's endothermic process. Okay? All right. Hydrogen gas and oxygen gas react violently to form water. That's an understatement. Right? Have you ever seen videos, old videos of the space shuttle taking off? You haven't seen it? Oh, you got to at least Google it and YouTube video and watch it take off. The main engines underneath the shuttle, there are 3 of them, are the ones that take hydrogen gas. Actually, it's liquid in that big orange tank on the outside, but by the time it gets in the engine, it's hydrogen gas. Plus oxygen gas from another tank, and they make water. And of course, at those temperatures, it's a gas too. Right? So we need 2 of these and 2 of these to balance it. All right. Which is lower in energy, a mixture of hydrogen and oxygen gas or water? Well, think about the system, right? The system would be this mixture. And when it reacts, does it absorb energy or give up energy? If this is the system, it's exothermic. It gives up energy. Q is negative, right? It gives up energy. All right. So if it gives up energy, let's say Q is exiting, that is, it's negative. Well, where did that energy come from? It was energy of composition. It was bound up in the bonds of hydrogen and oxygen. So when we think of before and after, if they have to be equal, the energy before and after, then the energy on this side is a certain value. Energy on this side is a certain value. And the energy due to this heat right here, well, this given up heat and this heat, this energy left over in these bonds, those 2 have to equal this one. Right? Does that make sense so far? Okay. If we're conserving energy, then this has energy a certain amount, this has energy a certain amount, and this is heat given off. The question is, which is lowering energy, this mixture or that product? Well, if this lost some energy in the process, this one must be lower energy. So the product is lower in energy than the reactants for an exothermic process. Okay? We're still chewing on it, maybe. Think of it in terms of energy balance. Right? You've got to have the same amount of energy out this way as you go ahead going in. And if this energy is given up, then the energy left over is right here, and it has to be less than that because you extracted some of it and went that way. Okay. So water has the lower energy in this process. All right, back to thermodynamics. This the parent for thermochemistry is thermodynamics. Thermochemistry is a subset of thermodynamics. And we mentioned that earlier. The total amount of energy that the universe started with is the same amount of energy it has now. And if we think about it in terms of it was all energy to begin with and matter came later, then we can actually, you can start any time in the universe's history, preferably once we had hydrogen and helium and maybe a little bit of lithium, but they were all the really light elements, right? Hydrogen, helium, maybe a little bit of lithium at the very beginning. And then the rest of that energy was left over. Well, if we go from there, then you can say that the total amount of energy change in the universe is zero. At least from that point on, it didn't change. Okay, now we're going to throw another curve at you. I think I'll leave that up there just in case. Internal energy. We want to define the internal energy of a system. So we're looking at this part of our model right here. So let's remove that so we can talk about just the system. The internal energy of the system, E, is the sum of all the possible energies of its particles. And we've defined the energies that are part of the system can either be potential or kinetic energy, right? So the total energy, the internal energy of the system, is the potential energy plus the kinetic energy. All right. We can also speak in terms of change in internal energy. If the internal energy of this system changes, we can follow the change in terms of either heat transfer out of the system or into the system, either way, right? Q, change in Q. So any change in the internal energy of the system is due to a movement of energy into or out of, right? And we observe the sign convention. If it's into, it's positive. If it's out of, it's negative. Or work. Actually, the summation of heat and work. Now, we also use the same sign convention for work. Right? If the surroundings are doing work on the system, like that, then that value is positive. And if the system is doing work on the surroundings, that value is negative. Okay? And work can be defined based upon this original definition of, excuse me, work equals force times distance. Now, what we're going to do is we're going to approach this surroundings working on the system working on the surroundings. We're going to start with gases because they're the easiest to equate to this function here. The force is kind of in terms of pressure, and the distance is in terms of volume. So we're going to relate the two. Force related to pressure and distance related to volume. Because in order for volume to change, the gas has to move either into a larger or smaller space, right? So there is change in distance, and pressure is a measure of force per unit area. We just need to do some algebra and figure out how do we define work in terms of pressure and volume for a gas. Then we can start using it. All right. So for any thermodynamic quantity, it's like any measurement. You have a number gives the magnitude of the change. Right? That's always the case. In any measurement, you've got a magnitude. You also have a unit of measure. Okay. So we need a unit of measure for heat predominantly, right? And that's the joule. And we also need to know which direction is it moving. We need a sign. So 3 components for thermodynamic values, right? The number, the unit of measure, and the sign. All right. We've already done this one. Maybe I should have moved that slide up a little earlier. This just reiterates the sign convention for everything is reference to the system. If it's being done on the system or it's going into the system, right? If you're working on the system from the surroundings or you're transferring heat into the system, then it's always a positive sign. And negative sign if it goes the other direction. Okay. All right. And I've already said that too. W is negative if the system does work on its surroundings. So I'm going to let Professor Dave talk in a minute. How would your gas do work on its surroundings? Let's say there's a force holding the gas in this volume, but it expands against that force. It's doing work on the surroundings, right? And it's losing internal energy as a process, as a consequence. Vice versa, right? If the gas were decreasing against the force on the outside, then work would be done on the gas. Okay, let's see what Professor Dave has to say. Oops, I have to start it manually.
Hey guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released. But it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define, but a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right. So, Professor Dave mentioned enthalpy. We're going to talk about this in more detail in a few more slides, so don't worry about it too much. Enthalpy and Q are related. It's kind of like temperature and heat are related. Q and enthalpy are related, but they're not the same. Okay. In the first place, enthalpy is a state function and Q is a path function. So it will be revealed when they are equal. Okay. All right. In this case, we're going to talk about, remember how we were trying to find out what's the relationship between the work function of force times distance related to a gas, pressure and volume. This is what we're going to derive here. So distance is the distance that the force travels, right? And force is here, right? It's being exerted on this piston. Actually, it's moving against a force. The piston is being allowed to expand against a constant force or constant pressure. And since that area, that piston is the same area before and after, then the force is proportional to the pressure. Okay. All right. So that's the force that's being applied, and the distance that is moving is that delta H. The distance that the piston moves is actually a change in volume, but since again, the piston is the same area, then the change in volume is proportional to the distance moved. All right, so pressure is constant. And now we're going to take this formula, work equals force times distance, and apply what we know about this particular situation. All right, so we know that if we take pressure equals force per unit area, correct? Then if we solve for force, then we get pressure times area. That way we can substitute this P times A into our work equals force times distance. So we can put this expression right there in the position for force. We also know that a change in volume for this particular example is the distance that the piston moves times the area, because it traces out a cylinder. Right? The delta H, the distance that it moves, Make this a delta H. The distance that it moves times the area is the volume of that cylinder. So if we solve this for this delta H, which would be D, all right, let me go back to D. If I solve for D, then that would be equal to delta change in volume divided by area. And we can substitute that in here also. So when we make those two substitutions, we get this equation. P times A for force times change in volume divided by area. And notice that area is in the numerator on one side and in the denominator on the other side, it cancels out. So what we have is this is equal to pressure times the change in volume. So there's our equivalence. We can calculate the work. Now, in this case, who's doing work and where's the system? Right? The system is the trapped gas. Okay. So the system is expanding against the surroundings. That means the system is doing work on the surroundings. And the value then would be negative. The value of work would be negative because the system is losing internal energy to do work on the surroundings. All right. Problem is the change in volume is going from a smaller volume to a larger volume. So it's expanding. We have a positive change in volume. Right? The change in volume for our example is positive. Pressure is constant, right? So it's a positive sign. Right? If it's got any value at all, this whole expression now then would be positive. But the system is doing work on the surroundings. So what's the sign for work? It's negative, right? Negative. Right? That can't be. You can't have a negative value here equal to a positive value there. Math won't allow it. Right? So we have to fudge. So what we do is we say, all right, in this expression, work is equal to negative pressure times the change in volume. That makes the signs compatible. Okay? All right. Now, we can also have different conversion factors. If we were to use standard units of measure for pressure and volume, well, not standard units of measure, conventional units of measure, right? Our Boyle's law we did, pressure was measured or converted to atmospheres, correct? So we had atmospheres here. And a change in volume would be in liters. So atmospheres, liters, or liter atmospheres would be a unit of measure for this. But the unit of measure for the SI unit of measure for energy is a joule. Right? And I showed you earlier how we got that, didn't I? Right. Kinetic energy equals 1/2 mv squared. So 1/2 standard for mass is kilogram, right? And the standard for velocity would be meters per second. Meters per second, and that's squared. So this is 1 joule. So that would be, the unit of measure then would be kilogram meters squared per second squared. Okay? So kilogram meters squared per second squared is the measure of joule. We need to know what's the relationship between liter atmospheres and joules. And there it is. 1 atmosphere equals 101.3 joules. Right? And I think that's in your useful information in the back. It would be that equivalence is there in case you need to use it. All right. So this one. Erase that, leave that there, get rid of this one. All right, so we just finished up the lecture section. Anybody need a break? Good. You need a break?
Yeah.
Okay. We'll come back with this slide as soon as you return. See, I'm up to, how far did I get? Slide 23. I'm about a third of the way. So we should be able to finish with it today. And I'll go back and insert the videos that we're going to see today, so that the sound will be better, picture will be better. It's really simple to do, so I don't mind.
Is this a lot harder than the rest of the chapter before? It's like it's kind of focused on its own.
Some students think it is, right? But it does have a considerable amount of math. Yeah, there are a lot of math concepts that have to be addressed in this one as well as in the gases. But that's the reason I do the gases first, because understanding how gases operate is essential to understanding anything about thermodynamics, and thermochemistry being part of that. In fact, I think that your textbook is set up that way. Gases are in chapter 5 and this is chapter 6. So the authors of this particular textbook recognized the fact that we needed gases early on. My introductory course, their textbook puts gases like chapter 8. And so they get all this other stuff before you get to chapter 8, and they're kind of lost once you get past about chapter 3. So what I do is I do 1, 2, and then 3, 4 for the first 2 exams. And then we skip to chapter 8 and get gases. Then we come back. It's odd though, because both textbooks are written by the same authors. We're going to lose power. Something shut down. The air conditioning unit. They might have to go up and reset the breakers, because it got quiet all of a sudden. Yeah, we're going to see somebody. We'll hear somebody walking on the roof in a few minutes. We probably won't feel the difference because it's always too hot in this room.
You know, most of the program here doesn't need chemistry, I guess the 1 or 2. Yeah, most of the health program.
Is that a question?
Mhm.
I think it depends on the program. I know MLTs need 1 and 2,
Okay.
both of them.
That's where I'm trying to focus. I actually started taking classes just because I haven't had any science classes. I have a bachelor, oh gosh, 15, 20 years ago. But I didn't, art major, so I didn't have any classes
Yeah.
for these. Well, I can start, but then I thought MLT is kind of interesting.
Yeah, and there's definitely a need for them.
Is there?
Yeah. Yeah, they our first cohorts before we lost our first director. Everybody had jobs when they got out,
Wow, that's great.
so that's a good sign. And then when Diane left, they couldn't find quick enough a director to take the program over. Or they wouldn't find, I don't know which would. Anyway, the program had to be shelved until we could find a director. And we had to get permission from Higher Learning Commission to do that. So they said, okay, you got to get somebody within this time frame. So we finally found somebody to run the program. And now it started back up again.
I guess I might have chemistry too next semester.
Yeah, as far as, yeah, I think it's part of the program. I think you can take the second chemistry while you're in the program. But you have to come in with a cohort, and the fall cohort, I mean, it's already going. So you'll probably have it before you apply and get in, or have you applied yet?
No, I think I need like a couple of science classes before I could
Okay.
apply. Yeah,
Okay,
I think the semester after next, I will be able to.
Okay.
apply.
well, unless something really drastic happens in the spring, we'll be having 102, 104. Sometimes we have 101, 103 again. It depends on whether there's students that need it. In fact, the cohort that's in there now, MLT, they took 101, 103 in the spring. And then we did 102, 104 in the summer. So that they could have all the chemistry out of the way.
Yeah.
And go in the fall cohort.
Science.
Yeah.
I'm surprised, I stayed away from it a long time. Yeah, I
Yeah.
didn't have science classes in high school.
Yeah.
I think I had like just a very basic biology
Okay,
in college, and that's the extent of my science.
okay.
This is it's
Yeah.
interesting. I mean, I enjoy it, but it's just a lot of work in such
Yeah,
a
it is.
small time.
And especially if your study skills are rusty.
Oh, yeah,
Yeah.
I'm sure it is.
Yeah,
Where I've been.
I know exactly where that's coming from. I was out, when I finished my master's degree, I was still working on LSU campus in a different department. And I decided I wanted to go for my PhD in agronomy, which is where I was working. And I said, okay, I found an advisor, and I started taking courses. And the first one I signed up for was physical chemistry. I said, what was I thinking? And it had only been a year since I had finished my master's, and my study skills had deteriorated that much. I had to really do some catching up.
I felt like all I do was study, and I only have a couple of classes, but a lot of memorizing different things. 'Cause I have
Yeah.
anatomy.
Right. Yeah. Well, there's a lot of memory work in chemistry in the very beginning, because you got to learn all the symbols. And periodically you have to learn these laws and formulas. That's one of the reasons I give you the formulas and useful information.
Yeah,
But if you work enough of the problems, then these formulas are just kind of ingrained,
yeah.
memorize it that way.
And that's what I was telling my husband. I'm like, and now I know what they're talking about when somebody talk about like calcium phosphate or, something like that.
Right.
That's pretty neat. Like, you aren't really paying attention, but where you do a lot of different.
Yeah.
Yeah.
I walk down the grocer's aisle, pick up a package, and immediately I turn it around and look at the ingredients. And you can understand what some of them are now.
But no,
Yeah. Some of them are kind of cryptic. They've got grandfathered in names, old names for stuff, and trivial names, we call them. Right. So you might have to go look those up and see what they are in our standard form. Right. But at least they're there. And when I was getting my master's degree in food science, one of our courses required that we design a product label and have everything that's legally required on it.
wow.
So it was So I knew the structure of the labels
Do
before.
you grow your own food after learning about like all that food science and
You don't-
what's all in our food?
You don't have to, right? Some of the students just went straight into industry. But when I transitioned over to agriculture, I sort of got a green thumb and I wanted to, so I had a garden. Actually, my supervisor was my boss. And north of Baton Rouge, he had 111 acres of property.
Oh,
I'd go up there on the weekends and he had a fenced in area that he let me garden. And he had a tractor with implements so he could do a lot of the heavy lifting for me.
that's pretty.
And the garden itself was probably 3/4 of an acre.
Are you originally from here or do you
Mhm.
live here like,
Now, I was born in Knoxville
oh,
and then moved around a little bit and family finally settled in Atlanta. And I grew up in Atlanta, right? And I didn't move out until I'd finished my bachelor's degree at Georgia State University. And then I went to Baton Rouge on my own.
cause, we like go on there for visit and stuff, but the weather is a completely different.
Oh, yeah.
Every year, so.
Yeah. Yeah, it gets hot in the summer. I did when I finished my PhD at LSU, I sort of educated myself out of a job because I was a research assistant and you can't have a PhD in that job. So they let me hang around. My professor retired. I was his last graduate student. So he retired and I closed out our research projects. They let me stay in several months to finish that out. And then I had to find a job elsewhere. So I went to Macon, Georgia and taught chemistry and physics at a private school for a year until they decided that they were paying too much for a PhD and they needed somebody with a lesser degree they could get by with, less money. And I found this position up here, just down the road, across from the Mine Academy.
Oh.
There's a USDA research center there.
Oh, I didn't know that.
In 2011, they shut that one down. So I took early retirement and ended up here. Okay. So which of the following performs more work? Let's see. There's our definition for work. Now, a gas expanding against a pressure of 2 atmospheres from 1 liter to 4 liters. Okay, so we've got a pressure, a constant pressure of 2 atmospheres. Okay, now we need a change in volume. So anytime you see a change of something, it's the final minus the initial. So the final volume minus the initial volume would be how we set that up. The initial volume is 1 liter, right? And the final volume is 4 liters. So the difference is going to be 3 liters, a positive 3 liters. Okay? So if we use that formula, W equals minus P times delta V, then we have a minus 2 atmospheres times a positive 3 liters. So the work done by the system, we have the sign here that tells us the system is doing work on its surroundings. And that makes sense because the gas is expanding from 1 to 4 liters. It's doing work on its surroundings. So it's a minus 6 liter atmospheres. Okay. We may not have to convert to joules. It depends on, right, so there's minus 6 liter atmospheres. How about the next one? All right, now we've got 3 atmospheres, a different situation. We got 3 atmospheres, a negative 3 atmospheres, and the work done times final minus initial from 1 liter to 3. So it's 3 minus 1. The final is 3 liters. The initial is 1. So 3 minus 1 liters. So this is 2, right? And this is 3. So this is equal to minus 6 liter atmospheres. Right, so it's the same. Right, it's the same work that's being done by both of these systems on the surroundings. All right. Let's see. Let me erase this. Okay. Determine the sign of delta E for each of the following with the listed conditions. Right. Delta E, remember, is internal energy. And it's work plus heat transfer. Okay. Okay, so an endothermic process that performs work. Determine the sign. And these are the different conditions. If we have an endothermic process, so endothermic process, that means heat is moving in, right? That's positive. Endothermic process. And work, we're not sure about yet. What we have to say is for delta E, and I'm going to write it down here also, plus Q. So for the endothermic process where see those bars on the outside, absolute value, right? The magnitude of work is greater than heat. Endothermic process performs work. Endothermic work on surroundings. That's what that means. So for this situation, if work, the absolute value of work is greater than heat, if W is greater than Q, heat, there we go. Work on the surroundings. So we are actually negative. Okay. If W is greater than Q, if this value here is greater than this value, then apply the sign, then this is more negative than this one is positive. Correct? If this one's more negative than that one is positive, then delta E is negative, correct? Now do that right. Endothermic, like that. Work on surroundings, like that. Negative, positive. If the absolute value of this one is bigger than that one, then the negative is, it favors the negative. Negative is bigger than the positive. So that means delta E is negative. Let's see if I got that one right. Yeah, okay. Now the other way around, right? If this one is greater than this one, it's just the other way, right? Because now this one is bigger than that one. And the positive overwhelms the negative. And that one should be positive. Okay. So how about the next one? Work is done on a gas and the process is exothermic. So it's exothermic. And work on the system. Okay. Now if we get W greater than Q, we're going the other direction. Exothermic means this is negative and this one is positive. So if this one is bigger than that one, then the sum of the two is positive. If the absolute value of work is greater than Q, then what we have is a positive value. And if we go the other way, then it turns negative. Okay? All right. Now we're going to talk about enthalpy. This term right here. Try to explain the difference between heat transfer and enthalpy. Let's see. Okay, there should be enough room. First of all, there are different values, but they do have a point of convergence. Right? And we're going to try to explain that. By definition, Q is the amount of heat transferred to or from the system. Right? It's a measurable quantity between surroundings that are warmer than the system or systems warmer than the surroundings. So you get heat transfer one way or the other. Just parenthetically, we can also transfer energy by work, either one of them. That's why Q plus W equals delta E. And there you are. Now we're going to talk about enthalpy. Enthalpy, think of enthalpy as a potential, a thermodynamic potential. What is the potential of a reaction to produce energy or absorb energy? Similar to internal energy. It's essentially a measure of potential heat energy in the system. So, and we define enthalpy in terms of internal energy. Enthalpy is defined in terms of what's the internal energy, and then what happens to this term, pressure times volume. And in this case, either or both pressure and volume can change. Right? That's the definition. Enthalpy is defined in terms of internal energy and pressure volume changes. So, by my way of thinking, pressure can be anything and it can change, right? But the volume may not change. Right? If it's a liquid or a solid, volume probably won't change, but the pressure could change. All right. Now, if it's a gas, then they can both change very easily. All right. So if we take the equivalence of what this one is right here, stick it in there, then we get Q plus W plus delta PV. That's enthalpy. Now, if the process takes place at constant pressure, then we can pull this P out here because it's no longer delta. It's not changing. So if we pull the P out here, then we're only allowing volume to change. Right? Only the P. Only the P stays constant and the volume is allowed to change. So that's what we get with that little move. Okay. All right. Now, if W is also equal to minus P delta V, where we have a constant pressure. So if we substitute this one for W, let's see. Oh, I didn't write it up here. Right, we're at this point, right, where we have Q, it's G, that's not Q, Q plus W, plus P delta V, and we substitute that one in for this one right here, then we get Q minus P delta V plus P delta V. And that term right there drops to zero. Okay? That's only if pressure is constant. If pressure is constant, then this is true. And in this case, whenever a process or a reaction is occurring under conditions of constant pressure, then we can equate the change in enthalpy with movement of heat. And that's what you'll see whenever a chemist can conduct an experiment, a chemical reaction, under conditions of constant pressure, then they're able to measure the Q and equate that to enthalpy. That's the only condition. If we have to let the pressure vary, then you can't equate the two. All right. Moral of this story is it's easy to get delta H and Q confused. One is enthalpy is a state function, Q is a path function. So in fact, it's easier to calculate if you're going to calculate enthalpy for a given reaction or a change of some kind. It's easier to do this one because you don't have to know what happens in between. All right. Let's see. You're studying a process that takes your system from P1, V1 and T1 to P2, V2, T2. That sounds like a combined gas equation. There are a whole bunch of different paths that you can take between the two states. That's true. Along each of these paths, the Q and the W will differ. And so a different path gives you a different Q and a different W. Oh, this is saying what I just told you. Right? But no matter what the path, the delta H for the transformation is always the same. Delta H only depends on the initial and the final states. It's a state function. So we come up with this expression. If we want to know what's the delta H for a reaction, what we need to know is what's the delta H of formation from the products minus the delta H for the reactants. If we know that, then we can calculate the delta H for that reaction. And if we don't hold P constant, if P1 is not equal to P2, then Q and delta H are different. All right. So there, up to this point, that's what we've got. Delta H equals Q at constant pressure, and the delta H for the reaction is delta H for products, delta H for the reactants, minus delta H for the reactants. So now we've got some stoichiometry to look at. I think I'm going to have to erase more. Yeah. Well, let's just clear the board. As long as my eraser lasts, looks like it's starting to leave streaks. All right, so we have this equation, C3H8. And that's a gas, yep. Plus 5 oxygen as a gas yields carbon dioxide and water. 3 carbon dioxide and 4 water. Notice they're saying this is propane. If you burn propane, it's going to be exothermic, correct? But since this reaction is being studied under conditions of standard temperature and pressure for chemical reactions, then water is going to be in a liquid state. Okay, so we specify that up front. If we just let it burn, right, we know that water is going to be a gas. And you remember taking your Pyrex test tube, sticking it in the burner flame, and it fogged up. That was condensation of water on the glass. But for purposes of studying this reaction and using the delta H that they've given us, then the delta H for that reaction, this balanced equation, equals minus 2,221 kilojoules per mole of propane. And that's valid because 1 mole of propane is the starting point. we're going from here, whatever. When we put a delta H, assign a delta H for a chemical reaction, the equation should be balanced. And then this value is, if this happens, whatever those coefficients are, if this happens, that's what you get. Okay, this could be 2, 3, 4 on some other reaction. This could be 1, this could be 5, whatever the case may be. Once it's balanced and the value is given to you, then that value is for this one in terms of the balanced equation. Okay, so very often you'll see that part's missing because it's assigned to the balanced equation no matter what the coefficients are. Right? Okay, so assume that all the heat comes from the combustion of propane. All right. Calculate delta H in which 5 grams of propane is burned in excess oxygen. Right, so we don't have to deal with a limiting reactant. We have 5 grams here. And we want to know what's the delta H. This is the delta H for the reaction. We want to know the delta H under these conditions. Right? That would be 1 mole here, but this is not 1 mole. So we've got to do some stoichiometry. In order to relate this to that, we have to convert this to moles. Right, so what do we need? Molar mass. Right, 3 times 12.01 for carbon, 8 times 1.01 for hydrogen. Add them together. Let's see, 12.01 and 3 times is 3603, and then 8.08 for hydrogen. Let's see. There we go, 4411. This is grams per mole. So grams goes on the bottom because we want to cancel that grams there. Now we can divide that into 5 and we get 0.1134 moles of propane. Well, since this is 1 mole of propane gives you that, then we know that we can convert mole of propane, C3H8, and then kilojoules of energy. Right? For every 1 mole of propane, you get minus 2221 kilojoules. Okay. All right. So let's take that number, 0.1134 times 2221. That's going to be a negative number also. So that's negative 25. Let's see. Well, that's only 2 significant figures. Right? No, 3. Good. I get to keep 3. 2 kilojoules. Under these conditions, 5 grams will release that much. I didn't know I had to animate it. There you go. Now, if it had been some other relationship, say, if this had been 2 here and 5 grams, then we would have put this much energy for 2 moles of propane. Okay, so you still need to use the coefficients when you're doing the stoichiometry. All right, calorimetry. This is where we're going to get into measuring the heat of a reaction. Using our homemade device. Now they make calorimeters, and we've got a few of them in our stock, but I don't like them. They're made out of aluminum, right? So right off the bat, you've got energy that's being absorbed or given up by a metal, which is and plus aluminum doesn't like some of our reactants. Right? So that's why I use styrofoam. Okay, It's just, calor. Has anybody had anatomy and physiology? Okay, you know the 4 signs for inflammation? One is calor, heat, right? If it feels hot, a chance it may be an infection. Another one is rubor, right? It's red, right? Dolor would be, it's painful. And what's the 4th one? Calor, rubor, dolor, and tumor, swelling. Could be swelling. So if you got all those 4, you probably got an infection or an inflammatory response. So, and that calor is where that comes from. It comes from I think it's the Latin for heat. So metry means measure. So we're measuring heat. Science of measuring heat. Okay. Some terms. We want to be specific with some of our terms. No pun intended. They start off with specific heat capacity. I want to start off with just heat capacity. So what's the heat capacity of a substance, of any object or any substance? The heat capacity is the amount of heat absorbed or released let me see. We'll get this right. Absorbed or released for every 1 degree C change. So what that means is this is an extrinsic property. In other words, if you have more of something, if you have more mass, then it's going to take more heat to raise it 1 degree. Right? It does depend on the amount of substance. So this is an extrinsic property. The specific heat capacity is sometimes more useful. We will use this one, right, for determining the heat capacity of our calorimeter, but that'll come later. We'll talk about that on Thursday. The specific heat capacity takes this for every, say, amount of heat absorbed or released for every 1 degree C change and 1 gram. Yeah, 1 gram mass. Now, with that, it doesn't matter how much mass you have. It's going to have the same number. This is an intrinsic property. Okay. So for water, for instance, its heat capacity, its specific heat capacity is 4.18 joules. Joules of heat for every 1 degree C change and 1 gram mass. So that would be the specific heat capacity for water. And they usually, I think your book uses an S for liquid water. Okay. When I was going to school, we used C. The only reason we use C is because at that time, we were using calories instead of joules. So we had a little C here instead. But now it's a little S. So that's probably more information that you needed. Okay. All right. Now, this is specific heat capacity. There's also another term that's very useful in chemistry is the molar heat capacity. Molar heat capacity, which is also an intrinsic property. And all it does is this value is for a mole rather than a gram. So it'll be some value here, joules per degree C per mole. Okay. Sometimes that's more useful in chemistry because once you convert things into moles for your stoichiometry, then you don't have to deal with grams. You can convert it back to grams. I mean, if you got moles already, this would work better. So if two reactants in a solution at the same temperature are mixed and the resulting solution gets warmer, this means what? If they start off at the same temperature and when you put them together, they get higher, then it's an exothermic reaction. The reaction itself, the reactants are the system and they're giving up heat in the process. So that's an exothermic reaction. If they get colder, then it's an endothermic reaction. And that's why we put things in a double styrofoam cup, because we want to isolate our system from surroundings so that everything that happens stays in there. That way we can deal with it, right? Otherwise, we've got to do something about the surroundings, and then we've got to measure things. We've got to measure the surroundings to account for any movement into and out of. Oh, Professor Day is going to talk again. Let's see if he may introduce some new topics and we'll deal with it afterwards.
Hey, it's Professor Dave. Let's talk about calorimetry.
He knows a lot about the science stuff. Professor Dave explains.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water. And the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup, so you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
So this is a model of the design of our calorimeter. We've got two coffee cups together, styrofoam cups. We got a thermometer poking through a lid at the cover. I used to have a stirrer in there, but it turns out that some of the reactions we study are corrosive to the metal that I use. I don't have any plastic covered stirrers, so I just eliminated the stirrer and we use the thermometer to stir. If you're careful, you can do that. It also reduces the correction factor that's required for the heat capacity of the calorimeter, because the heat capacity of the calorimeter depends on several factors. So we don't calculate it in terms of grams calorimeter. There are too many different things involved. We just have the one, the C, where we have the Q equals C times the change in temperature. That would be for using the heat capacity. But the specific heat capacity is, let's see, did I erase it? Did erase it, didn't I? Is specific, wait a minute, that's not right. Just write it out here. The change in heat for using specific heat capacity is that value times the mass of the sample times the change in temperature. And if we look at the units of measure, right, do some dimensional analysis, Q should be in what? It should be in joules, shouldn't it, for heat? Well, S is going to be in joules per degree C gram. And mass is going to be in grams. Oops, sorry. Grams, and change in temperature is going to be in degrees C, right? So these are in the numerator, those in the denominator. Cancel, 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 cancel. We're left with joules. So that's one way to verify that your equation is at least right in the units of measure. Okay. Now, when Professor Dave was describing a way to determine the specific heat of an unknown metal, that's the way I learned it. Where you take the heat lost by the water is the same as the heat gained by the metal. Or the heat lost by the metal is the same gained by the water. But that's only good if you've got two factors where you can say this one is equal to that. If you've got several factors, and sometimes we do, then I like this better. This is my approach. Our coffee cup calorimeter is an isolated system, right? Everything that happens in Vegas stays in Vegas. So anything that happens in that calorimeter must add up to 0. Right? So with two factors, if the same amount of heat that's lost by the metal is gained by the water, then those factors cancel because they're equal and opposite signs. But this way, if you say everything that happens in that calorimeter is equal to 0, then you can have a heat term 1, you can have a heat term 2, you can have a heat term 3, on out to as many as you need. Okay, that's the way I approach it. But you also have to be careful with your signs. But if you are, then this works great. Well, we'll use that in a few minutes. First of all, we're assuming this is an isolated system. In other words, heat transfer into and out of are zero. But of course, the calorimeter itself absorbs heat or gives up heat. So we have to account for that also. So one of these terms is going to be for the calorimeter. And the other terms would be maybe for water, and then whatever else substance you put in there. I mean, the sky's the limit. But one of them has to be for the calorimeter. Unless we specify that the calorimeter constant is zero, then we can ignore it. And some of my problems do that. Just to simplify things. All right. So that's what we're saying. Everything that happens in the calorimeter must sum up to zero. Right, so there's our formula, specific heat times mass times change in temperature. Remember, delta is always final minus initial. And that, if you remember that, then the signs will work themselves out. Right? Grams, temperature, and there's my formula. All righty. Now, let me erase some of this. I'm going to need some space. Might as well erase them all. Okay. Let's do some develop some intuition. Okay. If you have a sample of water that's at 90 degrees, you got a sample of water and it's 100 grams, and it's at 90 degrees Celsius. And we've got another sample that's also at 100 degrees, it's 100 grams, but it's at 10 degrees. See? All right, if we put those two together, they're the same masses and they're the same substance. This one's starting at 90, this one's starting at 10. When you put them together, where would you expect the temperature to settle? Right, with the same substance and different temperatures, but the same masses, we would expect them to meet exactly in the middle with temperature, wouldn't we? So what's the middle of 90 plus 100? 90 plus 10 is 100 divided by 2 is 50 degrees. We would expect them to meet exactly 50 degrees in the middle. Okay. What if we start with 90 degrees, only now we have 500 grams at 90 degrees. Excuse me, no, 100 grams at 90 degrees, pardon me. And at 10 degrees, we have 500 grams. Okay, where would we expect the temperature to be here? Would it be in the middle? Would it be this side or this side? Well, it's the same substance on either side, but there's more of this one than there is that one. So it has more heat capacity here than here. So we should expect the temperature to be closer to 10, right? It should be somewhere in here. Okay, what exactly is that temperature though? I had a slide set up like that for it and it disappeared somehow. So I'm gonna have to do this one by hand. So if we take that 0 and we have a Q for this one and a Q for this one, and we're not even considering the calorimeter at this point, just the two Qs, right? So Q1 plus Q2 equals 0. Well, Q1 is going to be specific heat of water times its mass times change in temperature. And Q2, this is going to be 1. This is going to be similarly for 2. Okay, remember the specific heat of water? What was that? 4.186. I left out 6 before. And this is joules per degree C grain. Okay. Mass. The mass on this side is 100 grams. What's the change in temperature? Well, we know that the final temperature is going to be something over here. So the final temperature is the unknown. We don't know what the final temperature is yet. Minus the initial temperature, which was 90 degrees, correct? Okay. That's Q1. Q2 has the same specific heat, joules per gram degree C, times the mass, which is 500 grams. And then this is delta T. So the final temperature is going to be the same for both of them because we just mix them together. So when they equilibrate, they're going to be at the final temperature. So this is going to be the same. But it starts off at 10. Okay? That's the thinking part. The rest is number crunching. We want to find out what that value is, right? Okay? So I know I'm going to run out of room down here, so I'm going to take this calculation and move up here. All right, so what do we got? Well, we've got to multiply this one times that one, and then multiply it by this, and then multiply it by that. So what's 4.186 times 100? 1, 2, 418.6, correct? Yeah, 418.6 times final temperature. Okay, and then minus 90 times that, because we got this times that. Right, we're expanding this parentheses. So what's 90 times 418.6? I don't know. I have to calculate it. 418.6 times 90 is 3767. 3767. Okay. Now, what's on this side? Well, we got 4.186 times 500. Times TF. And that's 2093 times final temperature. And this is going to be minus 10 times that value. So that'd be 2093. Okay? Let me check this out. Yeah, that's 90. Oops, I'm off by there. We do that again. 4.186 times 100. Okay, it's this one. 418.6 times 90. Yeah, 37674. 37674. Okay, there we go. All right. So now what we have is these two unknowns and these bare numbers. So since these are positive and these two are negative, why don't we put these together and move them to the other side? That would make them both positive, wouldn't it? Okay. So let's see. 3767. Let me roll these a little bit. There we go. I can add those together. So I get on this side. That didn't look right. Hold on a second. 37674. 37674 enter. And 20930 is 58604. on this side. And on this side, we have this one plus that. So 418.6 and 2093. And this side is 2512 TF. So TF is equal to this one divided by that. Okay. And I get 23 degrees C. Okay. All right. Yeah. The slide should have been right in there. I'm going to have to replace that. Be sure everything's updated in Brightspace. I think your copy may have. Yeah, it's got it in there. Yeah. I need to fix the, there was a glitch of some kind in that one slide. I got to see if I got a backup somewhere I can insert it again. Okay, so this is the temperature of water under these conditions, right? When it reaches equilibrium, 90 degrees at 100 grams at 90 degrees, 500 grams at 10 degrees, both water, put them together, and you end up at 23, which is, right, if this is 50, then it's on this side. So our qualitative assessment is true once we calculated the value. All right. So I think this one does have the slide intact when we go to the next one. In this case, we have our calorimeter in 50 grams of water at 10 degrees. So now we have 50.0 at 10 degrees. And on this side, we have an iron ball. So on this side, and an iron ball with a mass of 50 grams and a temperature of 90 degrees. Here we go. The specific heat of water is 4.18. Well, I think I used 4.18 in that case. And the specific heat of iron is 0.45. So it's about a tenth. The specific heat is about a tenth. So what does that mean in practical terms? If the specific heat is that much lower, then a certain amount of heat delivered to both of them would do what if they have the same mass, which they do? Which one's going to change a greater change of temperature? The iron. It has a lower heat capacity. So the same amount of heat is going to make its temperature change more. All right. So calculate the final temperature. Is it going to be between 50 and 90 or at 50? It's not going to be at 50 because they have different heat capacities. Between 10 and 50. I think it's going to be on this side here because water has a higher heat capacity, then it's going to change the least. Right? It's going to move from 10 over this way, whereas this one's going to move from 90 over that way. More change in temperature. All right, so the next slide, oh, it tells you the temperature there. Oh, here we do. Now we're going to do the calculation. All right, so for this one, we have the Q of water and the Q of iron, and we're going to ignore the calorimeter for the moment. All right. So there you have the water calculation first, then the iron calculation second, and here we input the values. Right, so the heat capacity of water is going to be 4.184. Where did I get 4? Oh, well, it shouldn't be that big a deal. What does our useful information say? Heat capacity of water. Look back here at useful information. Heat capacity of water. 4.184. So that's the one we're going to use. 186 was, well, it gave us the right answer, but it could have been a little bit off. All right, so the top one next to the 0 is going to be for water. Second one's going to be for iron. Notice we have two different specific heats. We have the same masses for the two, but we have two different temperature changes also. All right. Now, if we multiply the heat capacity times the mass for each one, that gives us 209.2 times temperature and 2092 for the actual temperature of water, 10 degrees. We do the same thing for the iron. And then we just solve for a final temperature. And that's where we get 18 degrees. Okay. So really, the trick to doing these calorimetry problems is setting them up correctly. Right? The math is not that difficult. You have to set them up correctly. Okay. Now we've got this idea called Hess's law. Hess was a chemist, and he was interested in determining beforehand whether a reaction would be exothermic or endothermic, and particularly if it was going to be extremely exothermic. He wanted to know in advance, right? So we could take safety precautions. Because if a reaction is going to be extremely exothermic, but you still need to study it, then you would scale it down to very small amounts. Like if you wanted to study nitroglycerin decomposition, that you want to use very, very small amounts in a very strong container. So Hess's law tells us that we can calculate the enthalpy of a reaction simply because enthalpy is a state function. So if we combine two or more equations and use the correct rules, we will end up with our target equation, and we can determine the enthalpy for that equation without actually doing the experiment. That's what I just said. And this, the reason 2 is to look ahead to what the reaction is going to be. And reason 1 would be look ahead. Reason 2 would be safety issues. Oh, Professor Dave is going to tell us about Hess's law.
Professor Dave here. I want to tell you about Hess's law.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. There are two ways we can use tabulated thermochemical data to calculate the delta H of any reaction. The first way requires that we manipulate thermochemical equations in specific ways. So let's be aware of some rules. First, if a reaction has a particular delta H, the reverse of the reaction will have the opposite delta H or the same number with reversed sign. Second, if molar quantities in the equation are multiplied by a coefficient, so is the delta H. So if you double all the substances, double the delta H. These are things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know about the change in enthalpy associated with a reaction, like this one. But it is difficult to measure experimentally. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want. The first reaction provided has carbon graphite on the left, which is where we want it. But the equation we want has 2 moles of graphite, so let's double this one. We get 2 moles of everything instead of 1, and we double the delta H. Next, this other one has CO on the right where we want it, and in the right amount. So all we need to do is add these equations together. The O2 and CO2 will cancel because they are present in the same amounts on both sides, and we are left with the substances in our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary as long as we change the delta H associated with it in the appropriate way. Then we add or subtract the equations as necessary to give us precisely the equation in question. The delta H you get by doing the arithmetic will be the delta H for the reaction. Another way to calculate an unknown delta H is to use standard enthalpies of formation. This is denoted by the following symbol, and it represents the enthalpy associated with forming 1 mole of a substance from its respective elements in their standard and most stable state. Most stable state means the most common allotrope, or physical form of an element. So carbon graphite instead of diamond, diatomic oxygen instead of ozone, and so forth. Standard state just refers to standard temperature and pressure, which is room temperature and atmospheric pressure at sea level. That's what is meant by the degree symbol. We can calculate the change in enthalpy for a reaction by adding up the standard heats of formation of the products and then subtracting the sum of the standard heats of formation of the reactants. The heats of formation can be found in your textbook or online, and you just plug them in, multiplying each value by the coefficients in the balanced equation. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right. So Hess's law basically says if you have a target equation, one you're interested in, you can use 2, 3, 4, as many equations as you want. As long as you follow the rules, you rearrange them as allowed, and make changes to the delta H, depending on your changes to the equation, so that when you add those equations together, you get your target equation. And that's all possible because delta H is a state function. It doesn't matter how you get there. We got there through this reaction, that reaction, that reaction, that reaction. Boom. Okay. All right. So for this one, let's see. Does this one have animation with it? Yeah, sort of. That's good. So this reaction also can be carried out in 2 distinct steps with enthalpy changes designated by delta H2 and delta H3. So the first one, if we take nitrogen gas, oxygen gas, and produce nitrogen monoxide, then the enthalpy change for that reaction as it is balanced is 180 kilojoules. It's a positive value. That means it's endothermic. Oh, by the way, standard temperature and pressure now. Remember, standard temperature for gases was 0 degrees when you're doing those physics types of arrangements. But for all other chemical reactions, standard temperature is 25 degrees. Okay, so let's look at this one. We've got 1 nitrogen in that one. We've got 1 nitrogen in our target equation. That's good, right? The nitrogen monoxide on the right-hand side, but there's no nitrogen monoxide in the target equation. So we're probably going to need another one. So that's where this one comes in. This equation, 2 nitrogen monoxides plus an oxygen yields 2 nitrogen dioxides, and its enthalpy is exothermic. It's negative. Now let's see, what would happen if we try to add those together? Are we going to get the target equation? Well, let's see. Those nitrogen monoxides cancel. That's good. And we've got 1 nitrogen here, 1 nitrogen there. We've got 2 oxygens, and 2 nitrogen dioxide here. So we didn't have to make any changes to the equations or to their enthalpies. Now we can just add them together. And we know that our target equation will give us an enthalpy of 68 kilojoules for that balanced equation. That is 68 kilojoules per mole of nitrogen, or 68 kilojoules for 2 moles of oxygen in that reaction, or 68 kilojoules for 2 moles of nitrogen dioxide produced. All right. This is how it would look if you put it on a graph. Kilojoules on the y-axis, and we're just from left to right, the progress of the reaction. For the 2-step reaction, the one where we added reactions together is on the left-hand side. And on the right-hand side, we're saying that we need to add energy, right? It's a positive value. That means it's endothermic. And we get the same values for either the 1-step, that's our target, or the 2-step that we use to get to our target. All right, these are the rules stated again. If you reverse the reaction, change the sign of the delta H. That makes sense. And if the reaction is going backwards, then instead of giving up heat, it's going to absorb heat, or vice versa. If you multiply the entire equation, balanced equation, by a factor, you also multiply the delta H by that factor. Let's see. What if we have these 2 equations? Now, Professor Dave mentioned one other thing, heats of formation, right? I think we have a separate slide on that, don't we? Heats of formation. Yeah, it's coming up. So hold on, we'll get there. So if we have the following data, like ammonia decomposes, 1 mole of ammonia decomposes into a 1/2 mole of nitrogen gas and 3/2 of hydrogen gas. With that delta H, it's an endothermic process. If we combine hydrogen and oxygen to make water, like we did earlier, it is an exothermic process that makes a lot of energy, 484 kilojoules for that reaction. Now, what's the delta H of this reaction, where we combine nitrogen and water to make oxygen and ammonia? Right? Do we have enough information in those first 2 equations? Well, let's see. We do have nitrogen, we got ammonia, we've got oxygen, and we've got water. Okay. We have hydrogen in the top equation, we have hydrogen in the bottom equation. So if we play our cards right, we can get rid of the hydrogens when we add these 2 equations together. So next step. The best way to work these types of problems is to work backwards. In other words, you've got your target equation, then you want to go looking for, in the given equations, which ones actually give you the information that you want, and then manipulate them as required, either reverse them, multiply them by a constant value, in order to, our end goal is to add all the equations together and get the target equation. All right, and that's what I just said. Okay, in this reaction, we need to reverse the 2 equations because we need ammonia on the right-hand side, we need oxygen on the right-hand side. So we're going to flip the equations and change the signs. That's what's been done in these first two right here. Okay. But we need to multiply the reactions by factors in order to get the right number of ammonia molecules, for instance, like 4 times the top one. And we need 3 oxygens, so we must multiply the bottom one by 3. Okay, and we get these two equations at the top. Now, if we add those together, are we going to get what we're looking for? Right, there are 2 nitrogens. There's 6 hydrogens here on the left and 6 hydrogens on the right, so they're going to cancel. There's 4 ammonias on the right, 3 oxygens on the right, and 6 waters on the left. So I think when we add them together, we're going to get what we need. And we've also been tracking our delta H's with reverse signs and constant multiplications in order to get those two values, minus 184 and plus 1452. Add those together and you get a reaction that is endothermic. You have to add energy. So what does that mean in terms of the reaction itself? Which side has more energy? The product side. We're adding energy to the system, which is nitrogen and hydrogen, to get oxygen and ammonia. We have to add energy to it, right? It's a plus sign. So it's endothermic, and we add energy to it. So the right-hand side has more energy than the left-hand side. Okay, now standard enthalpy of formation. This delta H, of formation, standard. That little 0 means standard conditions. That is 25 degrees, 1 atmosphere, and if concentrations are involved. Concentrations would be, let's see, what's my abbreviation for that? And just see, I just say concentration equals 1 molar. 1. There we go. If necessary. Okay, what you need is the most stable states of the reactants and the most stable state of the formation, or the required formation. So you start with, over here on the right-hand side of the arrow, and you put 1 mole of whatever you need. Say we wanted a standard heat of formation of oxygen. 1 mole in its standard conditions would be a liquid, right? And there's 1 mole of that. Now you go back to the left-hand side and say, all right, you can't touch this after that. Right? It's 1 mole of that compound. That's it. Now you have to stay on this side. So this is where we sometimes have to use fractional coefficients. So we're going to have hydrogen in its most common and stable form, gas, and oxygen in its most common and stable form at standard conditions, which would be H2 and O2. So how many oxygens do we need over here? Well, we only need 1. We got an O2, but we only need half of that. Correct? Okay. So we've got 2 here, right? So we're good. That would be how you would write the balanced equation for the standard heat of formation for water from its elements. And we always use elements here, element. You find those from here. Let's put them over here. All right, so there you give standard pressure for gas, 1 atmosphere, solutions are 1 molar, pure substances are either liquid or solid, and for an element, it's either a gas or solid, could be a liquid, right? Right, there are 2 liquids at standard state, aren't there, in the periodic table? Mercury, what's the other one? Don't remember. Bromine and mercury are liquids. at standard state. All right. So what we're saying with this reaction, okay, now we're away from the standard formation right now. We'll come back to it. What we're saying is that in order to form products from the reactants, we're hypothetically saying in step one, we're busting that methane molecule apart into carbon and hydrogen, right? That's what we're saying right here, right there. We're breaking it apart into carbon and hydrogen. And here, we don't have to break the oxygen apart because that's standard state. Right? Then when we put them back together, we're combining carbon and oxygens to make this, and we're combining hydrogen and oxygen to make water. And then if you take the standard heats of formation for each of these elements to make the compound, then you can add them together and get the heat of reaction. All right. This is rehashing information that's already been given. All right, so if we're actually going to determine the enthalpy under standard conditions of any reaction, then what we need to know is what's the standard heat of formation of all the products. That's what this sigma means. That's the sum of all the heats of formation for however many moles of the products times each one of their standard heats of formation for the products. And then we subtract from that the sum of all the standard heats of formation of the reactants. Okay, that's your formula. Products minus reactants using their standard heats of formation. Now, what this N means is, since the standard heat of formation is based upon only 1 mole of the compound, then if your balanced equation says 2 or 3 or 4, you have to say that times whatever the standard is because you're using more than 1. Okay. The standard heats of formation for elements is always 0. So if you have elements in your equation, let's back up. Like there, where you have oxygen in that arrangement, it has no standard heat of formation. It's given the value of 0. All right. How about this one? Sodium, 2 sodiums plus 2 waters, and these are standard states, yields sodium hydroxide in solution and hydrogen gas. Okay. That's a typical, very energetic reaction. Okay, that's the one you use if you want to crack the bottom of your neighbor's swimming pool because their dogs bark too loud. So you throw a big chunk of sodium in their swimming pool, and it'll make that gas at such a high rate, and once it reaches air, it'll explode. Anyway, so sodium is an element, hydrogen's an element in its standard state. Those values are 0. So all we have to concern ourselves with is water times 2 and sodium hydroxide times 2. So the sodium hydroxide would be here, it's a product, right? It'd be negative 900 and negative 940, right? Negative 940 because it's 2 times that value. And then we would subtract the water because it's a reactant. And there are 2 of those also. So it's negative 572, correct? So this becomes positive, and we say positive 572, and that's an 8. And that's 7 from 13 is 6, and 5 from 8 is 3. That's a negative kilojoules. So that's what we should get. 368 kilojoules. Okay. All right. We're doing pretty good, actually. And I've been wandering all over the place. So it's good to have a lot of excess time. If my students can stand it. You're putting anybody to sleep. Y'all didn't have to work double shifts yesterday, did you?
I went to work at 3 o'clock this morning.
That's enough.
I ran over 4 hours of sleep.
If I get 5 hours of sleep, I'm doing good. And that, I think that's just a consequence of growing old, sleep less. In my teenage years, I'd sleep 10, 12 hours. Fossil fuels. Okay, let's talk about sources of energy now. All right, I don't have imagine there's a soapbox here. I'm gonna get up on it in a minute. Fossil fuels, by definition, are those energy containing materials that have been buried in the earth. They're fossilized. Petroleum, oil, natural gas, coal, those are all fossil fuels. Wood, right? It has more energy than its combustion products. So it's a source of energy. Hydroelectric, right? It's a source of energy based upon the potential energy of water that's been raised to a higher level. How to get there? By the hydrologic cycle, right? The sun heats up the lakes and oceans and evaporates the water. It moves, and when it cools enough, it drops at a higher elevation. Right? Usually, if you have, let's say this is the coast of California, and you go in a certain way, and the mountains go like that. Right? So this warm, moist air moves in off the ocean, and it gets driven up. And as it goes up, it expands and cools. Right? Boils. Charles' law, volume and temperature. And as it cools, that means it can't hold as much water as the gas. So it cools to where the water condenses and it rains, right? It forms clouds and it rains. Right? And it goes down, and maybe we built a reservoir here and you got water caught there. Well, if you put a dam, or just take the water from there, and you go to a place down here where you've got turbines, right? And the energy that was expended to get it up there now is released in these turbines, and it generates electricity. Right? So that's hydroelectric power. In our country, all the major sources of power, rivers predominantly, have been dammed and tamed for both hydroelectric power and for flood control. Right? We don't have any more major rivers that can be dammed. Right? We're stuck. That's it for hydroelectric. The other disadvantage to hydroelectric is most rivers are flowing fast enough so that their sediment load is continually being churned up, and it's carried by the water down to where it slows down, like into a delta or whatever. When you stick a dam in the way, right, it slows the water down, right? And as it slows down, it can't hold the sediment load; it drops out. And behind the dam, it starts to silt in, right? So you've really only got one choice. If you want to continue using that hydroelectric, you go in and you dredge it out. And it just depends on the river as to what sediment load is being carried as to how fast that happens. In Egypt, when they built the Aswan High Dam, Russia came in and built it for the Egyptians. It didn't take 10, 15 years. And that thing was almost completely silted in because the Nile River carries such a huge sediment load. Okay, nuclear power. Nuclear power simply uses that energy that I mentioned earlier. When you split an atom, at this point, nuclear means fission. You split an atom and the products weigh less than the reactants. And the difference in mass is converted into energy. Right? And that heat is used to boil water, produce steam, and that steam is driven through turbines, which drives the dynamo and produces electricity. The advantage to nuclear is, for those who believe in carbon dioxide as a pollutant, it produces no carbon dioxide waste at all. Right? So if you get in a conversation or an argument with a greenie, an environmentalist, and they insist on driving everybody back to the Stone Age by getting rid of all the fossil fuels, right? Well, just ask them this question: what's your stand on nuclear power? If they say they're against nuclear power, then you have my permission to call them a liar to their face, right? Because they're taking two sides and which are opposed to one another. Because nuclear power is not polluting in their sense. So if they're against nuclear power, then they're just trying to. They're not just trying to pull your leg; they're trying to subjugate you. All right. So, historically speaking, until the beginning of the 20th century, most of our energy was derived from wood. There are places on the earth that used to be lush forests. Now they're completely nude because wood was used for various reasons. I mean, it was used for fuel. Initially, when the steel industry started to get cranking up, they made charcoal from wood. They just put it in these big earthen kilns and heated it up with no oxygen. And it reduced it down to carbon, what we now call coke. And that was used to make steel. But they soon ran out of that one. So somebody figured out, well, why don't we do the same thing with coal? Right? And that's what we do now. Right? There are certain deposits of coal in West Virginia and some other states that are very, very high quality. They have low sulfur, low other contaminants, and those are ideally suited for metallurgy. So you take those and you make coke out of them. You remove all the mineral components, and you're left with nothing but carbon, charcoal, and that's what you make your steel with. But at the beginning of the 20th century, coal was king. And it wasn't until the middle of the 20th century when petroleum and natural gas, oil and natural gas took over for most products. And it's been that way ever since. Right? Coal still has its place, right? But it's not the king that it used to be. And nuclear, hydro and nuclear, they lump those together. The problem with nuclear is not the engineering. The problem with nuclear is humans. Right? You won't have a nuclear accident if you treat it with respect. And 3 Mile, everybody points to 3 Mile Island. It was almost China syndrome. They did release contaminants into the atmosphere, but there are other technologies that use nuclear as its base that are much, much safer. Thorium is one of them, but for political reasons and personal gain, uranium was chosen rather than thorium. Thorium can't run away. But if used properly, you cannot create a runaway reaction with thorium, whereas you can with uranium. And then, of course, the holy grail is fusion reaction. using hydrogen in a fusion reactor to make helium, and you get energy, abundant energy with no pollution at all. And they're still working on it. Right? There's several different technologies that are being investigated that I won't go into now. But we have plenty of the hydrogen that we need to do certain types of fusion. There are other types of hydrogen that are not common on Earth. They're more common on the moon. So maybe that's one of the things that they'll be mining if we ever get to that point on the moon, is getting this certain isotope of hydrogen that for various reasons is a good choice. Okay. So how about the Earth's atmosphere? Why so many people, well-meaning people, I mean, good intentions, right? You've heard the saying, the road to hell is paved by good intentions. Right? Well, some people actually do have nefarious motives for pushing this environmental cause, right? They want power and they want to keep it. Or they want money, which is Al Gore, basically. So they're basing the greenhouse effect on this very real physical process, right? The Earth's atmosphere is transparent to visible light from the sun. Right? It comes in with virtually no, right, there's the Earth. And here's the sun. And light comes through the atmosphere. This visible light. And it makes it all the way to the ground, to the plants and bare ground, or whatever the case may be. And it's re-radiated at a lower wavelength, infrared, usually. Infrared, though, is readily absorbed by some molecules in the atmosphere. Carbon dioxide does. It does absorb infrared. And when it absorbs, remember conservation of energy? Right? When it absorbs that energy, light energy, it converts it into heat. Okay? Carbon monoxide does. Other hydrocarbons, like methane. Methane is exceedingly more efficient at absorbing infrared than carbon dioxide is. So they ought to be attacking methane, and some places they are. Right? They're trying to keep cows from farting or belching. See cows belch methane. Yeah, they belch methane. But by far, now water also absorbs infrared radiation. It's not as efficient as these, but there's a whole lot more of it. Right? So the overall impact of water in the atmosphere exceeds the impact of carbon dioxide by several orders of magnitude. Right? And they just conveniently ignore water unless it suits them. So what we ought to be doing is, if we don't want the greenhouse effect, we ought to be getting rid of water in our atmosphere. But then we turn the planet into a desert. Okay, so this trapped energy heats up the atmosphere. That's a good thing. If that didn't happen, we'd have a snowball Earth. And some geologists believe that at one time the Earth was a snowball. It had a runaway ice age, covered the entire Earth. There were also times in Earth's history, geologically speaking, when the temperatures were much, much higher than they are now, by 10 or 15 degrees. And in those times, the carbon dioxide level in the atmosphere was about 10 times as much also. So it's also believed that that's where the coal and oil, the natural gas deposits came from. Right? There was so much carbon dioxide that the plants and the energy, the heat, right? The biochemical processes were speeded up with increased heat. And they produced more biomass than could be degraded at the Earth's surface. So they just fell over, they buried and buried and buried and covered and compressed, and then we get coal and oil. So carbon dioxide, as far as plants are concerned, that's food. Right? It's not a pollutant. Numerous experiments have proven that if you increase the carbon dioxide in the atmosphere of a plant, its productivity goes like that. So what they're trying to do, the greenies are trying to starve all the plants on Earth. Okay, so this is the main idea behind global warming. Now, if you really want to investigate a greenhouse effect, runaway greenhouse effect, go to Venus. It's hot enough on the surface of Venus to melt lead. And it is truly a runaway greenhouse. But it's got carbon dioxide 100 times greater than ours. It's also got other greenhouse gases like sulfur dioxide and sulfuric acid in the atmosphere. But we're nowhere near that problem. Okay, so if we do want to reduce carbon dioxide outputs, right? So here's are some ways that we can do it. Coal conversion, gasification. For the energy you get from burning methane or natural gas, you get more energy per ton of carbon dioxide produced if you use natural gas. So take coal, convert it to natural gas, and then burn that. And then, of course, you have a lot of waste. Right? You have the ash, right, from coal. Some coals have more ash than others. Anthracite, the hard coals, have the least amount of ash. Bituminous, the soft coals, have more ash. Lignite is just barely coal. Right? It's got a lot of ash. Plus lower energy content. Hydrogen as a fuel. How about that one? Right? All you have to do is take water. Take water and split it into hydrogen and oxygen. All right, so we got two here and two here. And now you got hydrogen that you can combine with oxygen in various ways and drive your vehicles or produce energy, whatever you want to do. All you need is a source of energy that's non-polluting that can be used to split water and give you your hydrogen. Hence, nuclear power. Right? If you use coal-fired plants, you're kind of defeating your purpose. And now you may be thinking, all right, well, what about solar and wind? Well, let's see, I think we're getting to that. Oh, by the way, various ways to use hydrogen. You can run it in an internal combustion engine. It's not as efficient, but it works. You can use it, though, in a fuel cell, would be more efficient, where you combine hydrogen and oxygen in something akin to a battery, and it produces electricity directly from their combination. That's what was used in the space program in the 60s and 70s. And fuel cells on those spacecraft, and they were very expensive and very short-lived and run at very high temperature. So they had to take special precautions. Some energy alternatives, right? Oil shale. We can get lots more oil from certain formations, geologic formations, if we use a fracking technique. So you pump fluids of various types down into a structure. They've got the ability now to drill down and then go at an angle and send that pipe out through the formation for miles. And then they pump this liquid down in there. Holes are in the pipe. They pump this liquid down there, and it goes in at very, very high pressure, and it cracks the rock and releases the confined gas or oil. And you can rejuvenate a spent oil or gas field by this method. That's why during Donald Trump's years, he turned the frackers loose. And that's why for that short period of time, we became energy independent. We were energy exporters. You know, now we're begging the Arabs to produce more. We're begging totalitarian regimes like Venezuela to produce more for us because we're unwilling to produce it ourselves. Well, Biden is unwilling to produce it himself. Ethanol, right? You can produce ethanol from various organic forms. In this country, it's basically corn. In Brazil, they've been doing it for decades. They've been taking basically sugarcane or other biomass type grasses and converting them into ethanol and running their vehicles with it. There's just one problem. It takes more energy to produce the ethanol than you get back when you burn it. So that means it's not economic. The only reason that producers of ethanol can survive is government subsidies. I mean, if we turn the free market loose on them, they'd be out of business tomorrow. And then we wouldn't have to run ethanol in our cars because it's hard on your engines. Methanol is another product. It has more energy than the products when you burn it. Seed oils. Seed oils would be something that you might use in a diesel engine. In fact, the original diesel engine, let's see, what was the guy's name? Hans Diesel, Fritz Diesel. He was German. Was designed to run on vegetable oil. We didn't convert our diesel engines over to petroleum products until later. So, and I've seen TV shows of diesel engines that are running on vegetable oil that you can get as spent oil from restaurants. Those that do a lot of frying, you can get that oil for nothing because then they don't have to dispose of it. And your diesel engine will run on it. Solar, photovoltaic, and wind, either one of those. They have numerous problems. One is they're not consistent. Right? You can't get solar and wind power enough to supply the base load for your electrical demand. It's only intermittent. Now, there are people working on, say, Elon Musk is working on huge battery storage facilities for storing lots of energy in batteries so that it can be bled out during low production times or on demand. I don't know how that's going. Right? If he's using lithium-ion battery technologies, probably barking up the wrong tree because it has some very serious problems. One is they catch fire. And I already mentioned that inefficient storage technologies are available for those. The other is it's not competitive economically. I mean, it takes you years, even decades, to recoup the expense of photovoltaic cells and wind turbines before it becomes economically viable. And by that time, the technology is about ready to be disposed of. So it's not economic unless the government subsidizes it. And then there's environmental hazard. Right? These photovoltaic cells in particular, and some of the wind turbine internal workings are hazardous materials. Right? So at this point, we just put them on a barge and send them to India, Pakistan, for those poor folks over there to pick through them and suffer the hazards of these materials. Right? So the hazardous materials of these solar technologies are more serious than, by far, than any existential threat from carbon dioxide. Then nuclear. Nuclear solves all these problems for the foreseeable future. We've got enough nuclear energy to last for centuries. I mean, and just fission, right? Just fissional products like uranium, plutonium, which is a man-made element. If they ever decided to come back down to Earth and use thorium, that would even take us further. All right, so nuclear is the answer for anybody who doesn't want carbon dioxide emission. Nuclear is the only way to go. That's it.